All right, good morning, everybody. Welcome to another exciting morning of Chem 1211 with your host, me, Dr. White. I have some important announcements to make. First of all, because of my back, the only time I could get physical therapy today was at a quarter to 12. So that means I'm going to stop at 11:15, relax. Next week, I'll make up the time so you're not going to cheat you out of your money. Well, no, I'm not Trump. Oops. But anyways, uh, oh, that was a good one. One for Dr. White. But anyways, we'll do it. So I'm going to end early. Another thing I need to talk about next week, Tuesday. Tuesday is election day. First of all, I hope you all vote. Remember, brave men and women have died so you can vote. And I will be putting in my vote tomorrow. I have an absentee ballot. There's a drop box about 5 minutes from my house. I've just been too busy, but this afternoon I already got it time to do my ballot, and I'll drop it off tomorrow morning. All right. Now, because of that, in Illinois, it's now a state holiday, which means I can't have class, which is a good thing for voting, so you should all vote. I know from the other school, a faculty member who had never voted before uh, registered and voted the same day. I'm not sure if you can do that election day, but go this week. There's early voting just about everywhere in Illinois, or at least suburban our area. All right, so what that means is we won't have class on Tuesday, but good news, this is a net course, so that means there's no actual class times. So what I'm going to do is, so we don't lose valuable time next week, I'm going to be having our Zoom meeting on Monday from 10 to quarter to 12. And if you can't make it, relax. I'll be posting the video like I always do. So if you can't make it on Monday, you'll still be able to watch Dr. White. Oh, look, in living color. Oh, I'm on a roll today. Look out. So again, let me repeat, no class next Tuesday. I will be holding it at the same time, same Zoom channel on Monday. But if you can't make it, just watch the video. All right, any questions before I get started? Okay, you know what I thought to start off with? No, you don't, because you can't read my mind, so I better tell you. And that is, let's do an ideal gas law. Let's have some fun with the ideal gas law. Remember, I'm a chemist. All right, everybody see the whiteboard, white screen now. Good. Let's do it. Let's have fun. And let's assume when you burp, all the gas is carbon dioxide. Therefore, let's do the following. And most of your burp is carbon dioxide, CO2. And let's take a look at it. Let me read it for you in case you can't decode my handwriting. First of all, 15 points. What is the volume of your burp if you burp 0.567 grams of CO2 at 761 torr and 37 degrees C? So if we look at this, I'm going to make you work this morning. The first thing I'd ask you to do is over here somewhere, write down just what are you trying to find and what are you given. That's all I'm asking you to do. Take a minute, go. What are you trying to find and what are you given? Don't do any equations yet. Too early. You'll do it. And when you're done, give me a thumbs up. All right, I think everybody's done. So let's figure out, what are you being asked to find? Volume. What are you given? Well, you got 0.567 grams of CO2. You're given a pressure. Pressure, torr, is a unit of pressure, 761 torr. And you're given a temperature, which is 37 degrees C. Now, once you do this, you never have to look at this again, because you've done the hard part of translating it into something easy. Now, if we look at this right here, notice we have a gas. Carbon dioxide is a gas. And is anything changing? No. The weight isn't changing, the pressure, the temperature, the volume. So immediately, plus hint, 15 points. Oop, I gave it away again. Bad, Dr. White. You use PV equal nRT. By the way, this will be given to you. And remember, P is pressure. If I can spell it right. Oh no, Dr. White's having a bad spelling day. Every day is a bad spelling day for Dr. White. And it has to be in atmospheres. V volume in liters. N equals moles. R is the universal gas law constant, 0.0821 atmospheres liter per mole Kelvin. And then T is temperature. In Kelvin. Now, I'll underline, I'm going to go fancy today. This you'll be given, and all this you'll be given in important information, test number 3. But you got to know how to use it. So now I'm going to ask you to do the next step using this equation. Just solve, don't put any numbers in, solve for volume. How would you solve for volume? Your turn. In teaching, this is called fading prompts. And when you're done, give me a thumbs up, or turn on your video and smile, or you can do both, or make a funny face. Remember, I'm just asking you to use that equation to solve for V. All right, everybody done? I think so. So let's do it. Now, I want to solve for V. That means I want it alone on one side. Oh no, P's in the way. So how do I get rid of anything? Remember, anything divided by itself equals the number 1. That means it's gone. So if I want to get rid of P on this side, because I'm solving for V, volume, well, I'll divide this side by pressure. But whatever you do to one side, you have to do to the other. P divided by P is 1. 1 times V is V. And I now know what I have to do, what equation I use to solve for volume. Now, I've got to start putting in all these variables. Well, what's N? N is moles. Yeah, but we have 0.567 grams of carbon dioxide. What do we want to get to? Moles of CO2. Ooh, guess what time it is? It's time for Dr. White to do the following. It's time to use your good buddy, your good friend, unit analysis. Oh, I love that. Hopefully you're not getting fed up with me doing that. Well, if not, just go like this. All right, let's use our good buddy, our good friend, unit analysis. How do we do that? Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Therefore, I have moles, CO2, grams of CO2. Remember, the molecular weight of a compound equals 1 mole of a compound. And the molecular weight is the sum of all atomic weights. So now we have to find the molecular weight of CO2. Well, the molecular weight of CO2, sum of all atomic weights, there's 1 carbon and 2 oxygen. Each carbon is, well, let's, hold on, hang in there. So I think you guys could use some practice based on test number 2. So hold on. All right. Does everybody see the periodic table? Thumbs up, people. Thank you. Why don't you find out what is the atomic weight, the 3 significant figures for carbon and oxygen, and then I'll do it. On test 3, just like test 2, under your name, will say, please use proper significant figures for all calculated answers, and it will also say, please use 3 significant figures for all atomic masses, just like test 2. Let's take a look. Here is carbon, 12.011. Keep the 1, keep the 2, keep the 0. Use the 1 to round off, that's 4 or less, so that's 12.0. Oxygen, 15.999. Keep the 1, keep the 5, keep the 9. Use the next 9 to round off, that's 5 or higher. Drop that, increase this by 1, that becomes 1.0. So the atomic mass for oxygen atom or element, the 3 significant figures, is 16.0. So we now know carbon is 12.0, oxygen 16.0, do the math, add it up, and I have 44.0. Remember, you keep the same number of significant figures in addition past the decimal as the number you're adding that has the smallest. Notice both of these are both 1, so I have 1. So for every 1 mole, it equals the molecular weight 44.0. 3, Dr. Whiteson is 3 significant figure. Rut. And there, one of these days I can remember to save this so I don't have to go through formatting this. All right, everybody see the spreadsheet? I hope so. I'll do the math. I notice this is the number I get. And I should have done this scientific. Well, I'll leave it like this. And if I round that off to 3 significant figures, I get 0.129. Forget about the zeros at the end. I'm artificially increasing it. Now, this is a multi-step calculation, and there are 2 philosophies. One, round off at each step. The other, wait till the end. I'm an each step person, but I'm not going to force you to do the way I do. So I'll do 2 calculations, column A and B, and we'll see if they're different. If they're different, both are correct answers. So if we look at that, and I'll write that down so I don't forget it. The number of moles up here is 0.0129 moles CO2. All right, so we got this done. R is the universal gas law constant, which if you look up here will be given to you. Remember, R is a calculated value and it's 3 significant figures. Next, oh, I have temperature. What do we need temperature in? We need it in Kelvin. And you'll be given on test number 3 an important information. Kelvin equals degrees C plus 273. So if I come down here, and if I look up here where I took the time to figure out what the temperature is, it's 37 degrees C. And if we do the math, that will be 310 if I did it correctly. Let's find out. And I did. Okay. Now, are we done yet? No. Because now we have moles, R, temperature, but now pressure. Now, if we look up here, pressure has to be in atmospheres. Pressure has to be in atmospheres. Common mistake on this problem, I'm going to show you me. Common mistake on this problem, students put the pressure in torr or millimeters of mercury. No, that's wrong. And it will always be wrong. It has to be in atmospheres to use PV equal nRT. I see a question. Sylvia, which one are you asking about, 3 or 4 significant figures?
It's for the answer, the 0.0129 moles.
All right, let's go back to that. Thank you for responding to my question. Thank you for your question. Remember, all questions are good questions. Now, if you look at this number, lead zeros are always not counted as significant figures. Therefore, integers are 0.0129 is 3 significant figures. So I did it right. Look out, I'm on a winning streak. Aren't you glad you asked questions? Because I am, because this way you're not going to get it wrong on a test. And also you'll learn how to do it for future use. All right, so now we have to do pressure. And it has to be in atmospheres. And you will be given on test number 3 important information. 760 torr equals 760 millimeters of mercury equals 1 atmosphere. This is a definition. Therefore, those 3 numbers are all exact numbers. What do we want to do? If we look up here, we're at 761 torr. And what do I want to get to? Atmospheres. And therefore, oh, I'm going to do it again. It's time to use your good buddy, your good friend, unit analysis. Love it. And how do you use your good buddy, your good friend, unit analysis? Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. What am I trying to get to? Atmospheres. What am I trying to get rid of? Torr. Now, I'm going to play winky dink on you. You figure out what numbers, I'll give you 5.6 seconds, what numbers go in this ratio. Hurry up, time's clicking. Put down your pens and pencils, hand in your, oh, we're not in a classroom. Just keeping up, practicing. All right, what goes in there? Use this right here. 1 atmosphere is 760 torr. Now, the 760 and the 1 are exact numbers. Therefore, this has 3 significant figures. Our answer should have 3 significant figures. And let's go to our calculator. And if I round that off to 3 significant figures, because I'm a round off at each step person, that's what you get. So if we come down here, we have V equals, and you don't have to rewrite this like I do, but I want you to clearly see what I'm doing. PV, V equals nRT divided by P. N, moles, 0.0129 moles of CO2. What's R? 0.0821 atmospheres, liter, mole, Kelvin. And then what's T? It's right up here, 310 Kelvin. This one, if on a problem, I would make that come out to 311. Let's make this 8, so it's 311, and we'll get 3 significant figures. Sorry about that. when I do things on the fly, things like this happen. For every test problem, I make sure something like that won't happen because that's playing tricks on students. Then we're going to divide it by the pressure, and that's 1.00 atmospheres. If you notice, moles cancel out moles, Kelvin, Kelvin, atmospheres cancel out atmospheres. We're left with liters. Yay, that's a volume unit. And now let's do our math. And if you notice, if we round both of these off to three significant figures, this one would be 0.328 liters. This would be 0.328. Well, this is unusual. It doesn't always happen. But if you round off either way, you get the same answer. Let's see if I remember that correctly. And I believe I did. So your answer for this 15-point question would be 0.328 liters. Remember, 1,000 milliliters equal 1 liter. And we had fun with PV equal nRT. And if you burp that, see this bottle is 710 milliliters filled up volume-wise, not water. But if you burp, you'd burp about half of this volume of the bottle as gas. Wow, that would be a big burp. Wow. All your friends would look at you and say, "Are you okay?" I wonder how loud that would be. Oh, that's a different course. We don't do sound in this course. Look out, Dr. White's in a real good mood. I think part of it is my back is very slowly getting better. Maybe tonight I'll be able to sleep in my bed. I've been sleeping in my laser boy. But anyways, that's how you do PV equal nRT. Now, one of the things I want to do a little differently, since we're going to end early at 11:15, what I want to do now is do the lab that. Oh, did I forget to put in 3? Thank you, Camille. Yeah, Dr. White. Hold on. Oh. Guess what? Round them off and you get 0.329. Thank you again for correcting my mistake. So let's go back here. Let's correct my mistake. And that's what you would get. Actually, Camille, thank you. And that's what you get. And guess what? That'd still be a mighty big burp. Ooh, remind me when we get to acids and bases, I'll tell the story a Chem 1211 student told me about her grandmother's burps. It's funny. All right. Any questions before we go to lab? And then after lab, we'll come back to lecture. Because I'm ending early today because I got to go to physical therapy for my back, I want to make sure I get the lab knocked out. All right, good news. I made a mistake when I did my syllabus, but if you look on Blackboard, when you look at the assignment I've talked about, and I put down Charles Law. Now, that's another school. We're going to do ideal gas law lab. Now, one of the nice things about science is you just don't say, oh, this is what I think is true. No, you go into a lab and you prove it. Unfortunately, in today's political climate, uh, certain people don't believe when science says this is the facts, that those are the facts. But that's how you do it. And today, you're going to find out, is Dr. White lying to you about the fact that PV equal nRT is a law? See, I might be lying to you, but I might. And how do you do that in chemistry or any science? You prove it with facts. So how are we going to do that? Well, that's today's lab. Let's take a look at it. Thumbs up, people. Do you see the ideal gas law lab on your screen? Thank you. All right. So this is in both PDF and also a Word document in the assignment area, Blackboard. And a very important law is the ideal gas law, PV equal nRT. And notice I was nice enough to give you right here, P is in pressure, P is pressure in atmospheres, V is volume in liters, N is the number of moles, T is temperature in Kelvin, and R is the universal gas law constant, 0.0821. Oh, I forgot to tell you in the last problem, common mistake on test number 3, students write 0.8. They forget the 0. Don't, please. So in chemistry, a law is always true. And today's lab, you'll determine if it's true. How do you do that? By using a chemical reaction to determine the volume of a gas formed at a certain temperature and pressure. And from the ideal gas law, if you know P, and you know V, you know R, because that's a constant, you'll know T, because you can measure that, you'll be able to calculate N. And from the chemical reaction, how much you make theoretically, which you learned how to do in test number 2, you can also calculate N, and they should be the same number. Now, important thing. When I say same number, that doesn't mean exactly. It's going to be real close, but it's not going to be exactly. How do you like this new demonstration? This is the first time I've ever done this. Aren't you people special? Anyways, if you don't get 0.00111, say you got 0.00115, in my book, those are the same number. If you're within about 5 or 8% of either number, that's good, especially since we're not using $100,000 equipment if we were in the lab. No, we're not. But turns out this is a very exciting lab. Now, how are you going to do this? Well, you're going to do, you can determine the number of moles formed should be equal to the number of moles of a key reactant. Now, for this lab, you're going to be doing, let me just check. Everybody see the lab on the screen, the chemical reaction? Thank you. All right. You're going to be doing the following reaction if we were in the lab, and we do this if you were at COD. You're going to react magnesium metal with, this is called hydrochloric acid. And what you get is magnesium chloride, then hydrogen gas. I don't have it here, but now I'm putting it in, and it's given off as a gas. And you'll be able to measure the volume of the gas when you make it. You'll measure the volume. The room temperature will be the same temperature as the gas. And finally, what else is there? the pressure. And the pressure we use as the pressure in the room. And in our room, in our lab, in every lab, we have an electronic device called a barometer, and you can measure the barometer. And that will be in millimeters of mercury torque. However, the barometer in our lab that we would normally be in isn't that accurate. So what I do is I go to Weather Underground in front of the class, because I got a computer with a projector, look up the barometric pressure for Glen Ellen, which you can, and Weather Underground. Then I show you how to calculate it in atmosphere. So let's go back to the lab. And you'll be calculating from PV equal nRT, you'll calculate N, because you'll have P, you'll have V, you'll have R, and you'll have T, and you'll have to solve for N. We've already done that Tuesday. Look at the video. And then from here, well, you'll also be able, how many moles of magnesium will equal the number of moles of hydrogen formed. Because remember the coefficient, 1 mole of magnesium makes 1 mole of hydrogen. And therefore you'll know the moles of hydrogen. You'll have the weight of magnesium, but you'll have to convert that into moles. So before we go any further, let's have some real fun.
We need USAA insurance for this.
No, time for commercial.
Goodbye. Dr. White, we can't see the video.
First thing you do
Oh,
next round is
no.
measure
Hold
the
on.
mass of
Whoever said that, thank you. All right. Can you see YouTube now with the balance on the screen? Thank you.
the magnesium strip. There's an alternate way to do this that gives you
You'll
more significant
measure
figures
that.
that's in the description. But for this particular experiment, we're
Okay, well, I'm
really
going to
not
skip
going for
ahead
intense precision anyways.
to the fun part. In the
And
bottom, you
as
have
the hydrogen gas, you
magnesium.
can see that red
in the
color kind of
beaker,
moving down towards
and
the magnesium.
You
And what
would do
happens is,
similar.
as that hydrogen
We don't
gas
use a core.
slowly mixes, it ends up reaching the point where it's
We don't need the volume either, because I'll provide that. And you'll see in a little while, bubbles. Come on, bubbles. Because what's in the liquid here is hydrochloric acid, and I had dirty magnesium. Oh, see the bubbles? Everybody see the little bubbles? Now they're getting bigger bubbles. And hopefully they'll pan up soon. And what you do is you let this react. More bubble, wow. And see how this is going down? You started a measurement here, and these are in milliliters. And you'd actually be doing this in the lab. And those bubbles are hydrogen. It's really cool to do that. It's unfortunate we're not in a lab, because I like doing this lab, and you would too. And you'll notice the volume is going down. Eventually it's all gone. And notice you can measure the volume here like in a graduated cylinder. I have you clamp it so it's straight up. And we do this in a sink in case you're messy. And we have them, each group has a sink. And that's how you get the volume of how much hydrogen. The gas on top here is hydrogen gas. And I'll let you look at the whole video at your leisure, because it's on YouTube. But I think everything's on YouTube except my high school graduation. Well, maybe not my bar mitzvah either. If you don't know what a bar mitzvah is, go to Google. All right, and here I have the same procedure that you follow, and you would have a thermometer and measure the water or the room temperature. Either way, it's the same. You'd measure the pressure. I'd give it to you, and you dispose of it in a proper waste container. Now, good news, I'm giving you the data. Now, here we have the initial weight of the magnesium, and you'll need that. I call that number 1. When I have a number here, and a lot of you in the lab I just graded, and by the way, this morning I posted the scores for the last lab, made a mistake. You looked at equation 1 and thought it was really number 1. No, when I have an equation, I'll have EQ like right here. And a lot of you got that messed up. All right, we'll have the initial volume of the burette, the final volume. The difference of these, 3 minus 2, is number 4, which is the volume in milliliters of the gas. I don't have it here, but this should be milliliters. We measure the room temperature with a thermometer, degrees C, and with the barometer, the pressure in the room is 755 torr, which is also the pressure of the gas in that tube. Now, first of all, you have to calculate the moles of magnesium used. And how do you do that? You take the weight of the magnesium up here, number 1, and divide it by the molecular weight of magnesium. I'll let you figure that out. And you can put the number in here, moles of magnesium. Next, how many moles of hydrogen did you make? Remember, moles of magnesium use unit analysis, moles H2 go here, moles magnesium go here. You learn this. We come up here to our balanced chemical equation, and we see 1 mole of magnesium makes 1 mole of hydrogen. And therefore, whatever the moles of magnesium are, will be the same as the moles of hydrogen, which is why I have number 6 is the same as number 5. Now, you have to calculate the temperature in Kelvin. How do you do that? Oh, Dr. White's being too nice to you. Remember, Kelvin is degrees C. And where do you do this? That would be number 7. Not number 7. Hold on. I don't even have this temperature up there, plus 273. Now, you calculate the atmospheric pressure in atmospheres. Remember this, and we just went through that in the problem earlier today, how to convert that. We did it earlier, so look at the video for a day earlier. I'm gonna make you work a little. And then the pressure in atmospheres of hydrogen is the same as the pressure in atmospheres for the room. And the temperature of the gas is the same as the temperature in the room in Kelvin, and the volume in liters. Now, 1 liter equals 1,000 milliliters, and we'll learn more about this in chapter 12. Therefore, milliliters gas times 1 liter per 1,000 milliliters, I'm using it, equals liters. So number 4 divided by 1,000 equals this. These are both exact numbers. So now we have everything you need. You have above there pressure in atmospheres, volume in liter, you have the moles. No, you don't, because that's what you're trying to solve for. You have R and T, and therefore, hint, I'm not going to show you how to do that. look at Tuesday's lecture to see, oops. And solve for N, remember R is this, and that will tell you how many moles of hydrogen. And if PV equal nRT is true, N here for number 8, N there, and N here, the moles, should be the same number, or better yet, number this one. The number of moles of hydrogen you calculate theoretically should be the same. Remember, my definition of same is not exactly, ooh, I've used this twice today. Aren't you lucky? Not really. But anyways, if you're real close, that's okay too. And there are questions at the end for you have to answer. Yep, I'm being mean again to you, but I've helped you out with all the calculations. And that's what I would do if we were in the classroom, because the lab book doesn't tell you that much. And that's today's lab. Remember, the ideal gas law lab is due next Thursday by the end of the day. And also, a couple of you are missing labs. Make sure you hand them in because of the virus. I'm not being like I normally would, which would be after 8 days, you got 0 points. Now I'm going to extend the deadline, really extend it, right off the screen. And don't tell anybody I'm being nice, okay? And with that, it's time for a break. I'll see you in 5 minutes. We're going to end early today, so just hang in there, home stretch. I got to go stretch my legs and back. See you in 5 minutes at 10:55. Actually, yeah. Time to start again. All right, let's get going. And by the way, guess what time it is? It's new chapter time. We get to do the next chapter. And what is that next chapter? Thumbs up, people. Do you see chapter 12 and 13 on your screen? Thank you. And that new chapter deals with, actually it's 12 and part of 13, part 1, because I combined them two, deals with solutions. And solutions is probably one of the more exciting parts of chemistry. All the chemistry I've ever done deal with solutions. So the question is, what is a solution? Well, a solution is a homogeneous combination of two or more substances in which each substance contains its own identity. So if you mix two things together, and guess what? They don't react, you have a solution. And if I were to take this water and put in some salt, shake it up real good, I would have a salt solution. No, I wouldn't, because it'd be, ooh, salty. But if I were to put some sugar in here and some vanilla extract and shake it up and real good, and now you'd have something that tastes real good. And this would be then a solution. Remember, a solution is a mixture of two or more things. Now, bet you never thought of this, but everybody inhale, let it out. Guess what? You were just inhaling a solution. I bet you never thought about that, but air is a mixture mainly of oxygen and nitrogen gases. And all around you, you're surrounded by a solution. Next time you're at a party and you see somebody breathing, or a Zoom party, I don't know if you've been to some, I have, they're pretty wild. They're usually a BYOB, BYOF, BYOWC. Bring your own booze, bring your own food, bring your own web camera. But anyways, tell them, you know, you're breathing a solution. No, don't. They'll kick you out of the Zoom meeting. But anyways, think about it. Air is a solution too. Now, when we talk about solutions, this is something important you should know. Oh, look, it even says it on the slide. When we talk about solutions, there's two main definitions of the components of a solution. One is called the solvent, and a solvent is the component of the solution present in the greatest amount. Again, the solvent is always the component present in the greatest amount. Now, the other components are called solutes, and a solute is a solution component that is present in a small or smaller amount relative to the solvent. So the component in a solution that's in the greatest amount is the solvent, and the other components are called solutes. Ooh, let's practice this. Well, let's look at air. Let's assume you have a sample of air. And if we look at the following, air is roughly 80 grams of nitrogen and 20 grams of oxygen per 100 grams of air. What is the solvent and solute in air? Well, the solvent, and I'll share, I'm going to let you try one too, is the component present in the greatest amount, which I hope you all agree 80 is greater than 20. So the solvent is nitrogen gas. What is oxygen? The solute. Remember, solvent, the component of the mixture present in the greatest amount. All the other components are solutes. So let me have you try one. All right, let's do this one. I might even make it 4 points. Rubbing alcohol is 70 grams of isopropyl alcohol, also known for those in the chemical industry, like Dr. White, is IPA, and 30 grams of water. That's a homogeneous mixture, meaning it's the same throughout. And what is the solute and solvent in rubbing alcohol? Your turn. And when you're done, give me a thumbs up. Because you can't do a thumbs out and down in Zoom unless you're on video. Everybody done? Going once, twice, let's do it. So what's the solvent? Solvent is the component present in the greatest amount. And we have two components. One is 70 grams, the other 30. I hope you all agree 70 is greater than 30. So the solvent in rubbing alcohol is isopropyl alcohol. And what is the solute? Water. And that's how you use solvent and solute. Oh, let's do one more. All right, let me decode this for you. A solution contains 100 grams of sugar, 50 grams of water, and 1 gram of sodium chloride salt. What are the solvent or solvents and the solute or solutes of this solution? Your turn, go. When you're done, give me a thumbs up or the high sign. Ooh, I just did a generation gap. If you don't know what the high sign is, go to YouTube and watch Our Gang. If you haven't seen Our Gang, you should, with Spanky and Alfalfa. And Spot, their dog. And who was the girl? Delilah, I think. Uh-oh, Dr. White's been brainwashed by TV. All right, let's do this. Question is, a solution contains 100 grams of sugar, 50 grams water, 1 gram of sodium chloride. What are the solvents and solute of this solution? There's only one solvent. That was a trick. And the solvent is the component present in the greatest amount. And I hope you all agree 100 is greater than 50 and 1. So the solvent, turns out, in this solution is sugar. And what are the solutes? Well, that's all the other components, which would be water and sodium chloride. And that's how you use and define solvent and solute. And you should know how to determine, like I just had you do, what's a solvent and what's a solute in a solution. All right, let's move on. Now, it turns out there are different types of solutions. And as I've mentioned, air is a solution. And when it's real humid out, air also contains water vapor. And later on this chapter, I'll teach you what the word water vapor really means. Next, we have liquids can be solutions, salt and water. By the way, next time you're in a bar and the bartender makes you a mixed drink, you can tell him or her, guess what? You've just made me a solution. By the way, bartenders do not like being taught chemistry. Trust me. And gasoline is a very complex solution. Now, certain solids can be solutions, and I won't ask on test, but the old dental fillings that were mercury amalgam were a solution of mercury with other compound. Because there's mercury in there, they stopped using it. It's dangerous. Sterling silver is a mixture. Your catalytic converter in your car has gas mixed with a solid, and that's a solid. As you notice, I move quickly on. I'm not going to ask you anything about that slide on the test. Now, there's certain definitions you should know. And one is the solubility of a solute. And that's the maximum amount of solute that will dissolve in a given solvent. A solubility of a solute is the maximum amount of solute that will dissolve in a given solvent. Now let's go out into the real world. No, I tried a shortcut and I should know. All right, everybody sees sodium chloride on the screen? Thank you. All right, this is Wikipedia. Wikipedia, I might have mentioned, so heavily policed by chemists, including myself, that it's been a number of years since I've seen anything really wrong for chemistry. Other things, no guarantee. Now, if you scroll down on the right side, you'll see identifiers, and then you'll see properties. And notice they have the molar mass, the molecular weight, and other things. And notice here, we have solubility of salt and water. And this tells you that you can put up to 360 grams of sodium chloride in 1 liter of water, If we look down here at number 1, I don't see it. It'll probably be what temperature you're doing it at, because solubility is also temperature related. And notice, I don't know why you need it, the solubility of salt and ammonia, and also in methanol, which is an alcohol. And that's how you do solubility. So solubility tells you how much, the maximum amount. You can't put one more molecule after that amount is reached. Now, factors that affect solubility are the solvent, like I just showed you. Is it water? Is it ammonia? What temperature? What solute you're using? Are there other solutes pressure? And sometimes even the pressure, atmospheric pressure. Now, if I look at the clock, it looks like this is about a good time for me to end the lecture so I can get ready to get my back fixed more with physical therapy. So with that, today is Thursday. I'm going to say an important thing. Remember, next Tuesday is election day. The school is closed, but because this is a net class, I'm putting the class on Monday. If you can't make it, I'll still post the video. So relax. I'm not cheating you out or anything. With that, I'm going to say goodbye. Kein gesund. I'll see you on Monday. I'll put out an email later today reminding everybody about the change. Don't forget to vote. Brave people have died so you and I can vote and be free. So please vote. I'm not telling you who to, but vote, because that's our special right as citizens. With that, kein gesund. Goodbye. I'll see you on Monday.